topics of each of two sessions. And the first talk is titled Robust But Relax Probing Model. Talk will be given by Nikolai Müller. Please start.
Perfect. Yeah, the slides. So yeah, you can hear me. So yeah, many thanks for the nice introduction and welcome to this talk where we basically want to relax the robust probing model. So I know this is a gadget session, but yeah, you have to wait until the end to wait and sorry to talk about gadgets. So it is basically not part of this talk, just at the very end. In the beginning, we want to talk a little bit about implementation attacks. So basically on hardware, so we consider a cryptographic device which executes a cryptographic algorithm under a secret key which is stored on the device. And as you might know from the side channel context, all these cryptographic devices emit some physical characteristics to the outside world, which can then be exploited by side channel attacks. So for example, problems are emitted power consumption, electromagnetic emanation, timing, sound, or temperature. So this should be, I think, basic knowledge since most of the talks we heard already at CHES. And we also know that there is light at the end of the tunnel and we have a countermeasure against it, which is masking. So masking aims at randomizing intermediates to avoid the dependency between the sensitive values and, in this case, the power consumption. We can apply this on the algorithmic level. So we can basically transform our unprotected circuit into a protected one, which is then secure against side channel analysis. So we don't have to think about our device, which is underlie to execute it. And yeah, as you might know, each intermediate is basically shared by using random masks, which are uniformly distributed for every execution. And yeah, just to show you a little bit what I mean in this talk here, we consider Boolean masking. And just to give you some notation, we start with a circuit which can implement any Boolean function you want with n inputs and in this case, m output bits, and with sensitive input x. And we just want to share it. So we define an encode function, which basically transforms our unshared input into a shared input based on the randomly distributed shares. Then we define a so-called circuit compiler, which transforms our unprotected circuit into a masked circuit, which then processes the shared input in order to compute a shared output, which we can then simply decode or transform back to our unshared output value. So, and as I wanted to talk about probing models here, we have, of course, to ask the question, how can we prove actually that our masked circuit is secure or does what it is intended to do? And for this, we have probing models. So as very basic intuition here, we can say, of course, we don't want that our adversary gains access to a complete set of shares. So we don't want that the adversary gets access to all of the shares of a secret value, so he cannot recombine it. And this is basically covered by the deprobing model. So to check if this property that our adversary don't get access to all of the shares holds, we basically define a formal adversary that can arbitrarily place up to d abstract so-called probes on wires of our masked circuit, which then probe a stable intermediate for each probe. So we then consider a circuit as so-called deprobing secure if the observed signals are all statistically independent of every secret. So let's make a short example here. Yeah, let's see here. So we consider a very simple circuit that implements basically one AND gate. So we have two inputs, x and y, and compute the multiplication x, y. So we start just by sharing it into two shares, so x0, x1, and y0, y1. Then we simply write down how we can compute the AND function. So just by computing the unshared AND and then on the shared variant to get two output shares. This we can then split, for example, into a computation which looks like this. And this we can implement in hardware so that it looks like this. Now the question arises, is it secure or not? We can try, we place a probe, for example, here on the output share Z0. And we can see that this probed intermediate, which we calculated before, depends, for example, on Y0 and Y1. So it's obviously not independent of our secret. So we can consider this circuit as insecure under our probing model. And what we can usually do to avoid this problematic is we can just add a random value here just to make it, again, independent of our sensitive value. So this is basically the basis for security proofs of masked circuits, which is a model which is well known and well studied here. But it has a problem because it assumes an ideal circuit, which is basically not the case in reality. I just want to visualize the problem shortly based on an AND gate. Here we can also see the notation for the rest of the talk. We consider an input sequence from two values, which I call here x prime x, for example, which just means we start in one state and switch to another state. So, for example, in this case, we place a probe on the output and consider one input sequence, which can look like this. So one input swaps from 1 to 0, the other one swaps from 0 to 1. On the output, of course, we would expect, again, a 0 line. So we would expect that the first state was 0, and again, the next state is also 0. What happens in practice? Yeah, it depends. We have a short look by considering the time it takes to make this transition on the input. For example, we call it here Tx for the x input and Ty for the y input. Now we assume, okay, Tx is a little bit faster than Ty. What happens? The first signal swaps to 0 before the other signal swaps to 1. We get a constant 0 line, which we can see at the output, which is okay. And if we measure, for example, the power consumption here, we can see something which looks like this when we just measure a filtered signal. So yeah, this can happen. But what happens now? We basically have the same input sequence, but just swapped on the inputs. So we would expect the same, but we don't get it, because now in this case, the first input swaps from 0 to 1 before the other one swaps from 1 to 0. So what we get is something like this, which we usually call a glitch. So you can see this is basically the same behavior when we just consider these stable signals. So we have 0 at the beginning and 0 at the end. But in the middle, yeah, something unintended happens, which we, of course, can see in the power consumption and which we can also probably distinguish by just observing a single sample in this power consumption trace. So what we can conclude from this? We can just conclude that basically the deep probing model does not hold really, because we don't get only the probed value, but we get also some values from before. So just values which contribute to this probed wire, which we, of course, have to consider in our adversary models here. So the intuition I already gave, we get more information than just probing a single wire. And yeah, how can we model this? For example, in a worst case way, by just assuming that a probe on a signal gives us all intermediates from before, until to the point where we can stop the glitches, of course. And this is basically done by the robust deep probing model, which extends the usual deep probing model. Yeah, for example, by considering glitches, but also by considering transitions, which are also discussed in this talk. So basically, we allow the adversary now to place up to these so-called robust probes, which have a special probe extension procedure I want to show in the following, which does just cover all this propagation back and all this consideration of intermediates, which we have to consider because of glitches. So we again consider our circuit from before, which implements the just the AND gate with the randomness here. And we again place a probe on Z0. So what happens now? We know that we get more information than Z0. And what we get is basically this back propagation procedure, because the glitches can propagate back unto the last synchronization point. So we have to do this with our probes. And what we basically get, I have to go once back. So what we get here is, again, Y0 and Y1. So insecure under the robust deep probing model. What we can do against it, we can place registers, which basically synchronize our intermediate values and stop the glitches. So now the propagation changes a little bit, as it has to stop at a register, and we don't get all the intermediates from before, and are safe so far. So this is, basically the point how we, at the moment, just check our circuits in a masked way that they are secure. What is the problem with this? The problem is this over-conservatism. So when we formally consider glitches, we consider them at the moment in all the way that they can occur, independent of if they do or not. So if you have a circuit that does not glitch, or that just glitched at some points, robust probing model does not care. It considers every possible glitch. So it could be the case that you have some circuits that are secure in practice, but insecure under this model, which we want to try to avoid because this is an overhead we don't want to have. So what we can do, or what we can, what I just want to show you. Like this. Yeah, we already know that this is not always the case, that we have this very conservative propagation. For example, I give a short input sequence, which is pretty easy here. We just basically keep our AND gate at a 0 value. What happens in our power consumption trace, on our signal trace, just a constant 0 line, of course. But this also happens for this input sequence, or this, and the last one, this one. So here we can basically see, okay, we have different states for our inputs, but we cannot distinguish them on the output. So when we place a probe on the output, we should not basically have this back propagation, because it's not accurate here. We cannot conclude this. So what we can see is that this information propagation basically depends on the process data. So it's not easy to say, okay, we have a glitch or not, it depends. And this is what we basically want to discuss in this talk. We want to see if we can adjust this model a little bit just to cover the data dependency of glitches. And if this sounds familiar to you, the reason is that the best paper did almost the same. So if you listen carefully to the best paper talk, you can skip the next, I think, 4 slides, and I can wake you up when it becomes a little different to them. So, but if not, we will discuss it a little bit and start again with the AND gate and just consider all the states and what happens if we probe the output Z. We just make it with a short table here. Just take some time to look at it. I will discuss the different cases which can happen here, which are basically 3. First of all, if Z toggles, so if we have some transition at the output, we can most likely get information about all the inputs, because you have this delay time. When the toggle happens, you can have glitches. This is basically the case where we assume that we get all the inputs here. So this is like in the robust deprobing model. It just propagates back to the inputs, and due to transition, it gets back to the consecutive state. So here we have X prime, the first state, and X, the next state. I just denoted this with P to have a probe here. So PX basically means a probe on X. So this propagation we have, for example, for all cases where it toggles here. Then we have a special case where the output is already unique, so we can conclude from the output what the input is. This is here given in the last case where we have a constant line on 1. So basically we know that both inputs had also to be a constant line at 1. So in this case, we can trivially also propagate back and get all inputs. But then we have the third case. If that constantly stays at 0, we cannot draw this conclusion. So in this case, we just consider, okay, we have the transition, so we can see, okay, we had 0 and we go further to 0, but we cannot propagate back to the inputs here. So based on this, we made a little formula, just a Boolean one that calculates if we have this propagation or not. So what you can see here in this f function is just that we assume that we have to propagate back if not both inputs, if not both states on one input is 0. So for example here, if X prime and X is 0, we have a constant 0 line on one of our inputs and we assume no propagation. In all other cases, we do. Sounds easy, and it is. There's only one thing that complicates this stuff a little bit, because what happens if our inputs are already glitchy? At the moment, we just assume that we have glitch-free inputs, but this is not always the case. In this case, something like this can happen. We have a glitch at the input, we have a constant 1 line at the other input, and it propagates to the output. The glitch propagates. So this can happen, but basically here holds the same. If we have a constant 0 value at the other input, the glitch is basically stopped. So what we did to cover this is, we just made another formula which considers glitches. So we first adjust the f function to say, okay, if there is a glitch on my input, we possibly have to propagate back our probes. So in this case, we have to assume that we get more than just the output. So this we assume by setting another variable, which is called gx and gy, just to indicate if we have a glitch on x or a glitch on y. And to get this glitch, we calculate another function, which we call g function here, which is basically relatively simple. The first 2 monomials just indicates, okay, here a glitch manifests if we have no glitch at our inputs. These are the cases I can show you back. Second, here. These are just the cases where we get a glitch on our output if our inputs do not glitch. And the other cases here covered with the other two monomials, yeah, here are just the cases when we have a glitch at our input, but the other line is not constant 0. Then we, of course, have to propagate the glitch. So this can we do for the AND gate, but we can also do it for other gates. Again, we do it for the OR gate. And I think I can go fast over it because it's basically the same, but with some difference. We have the same three states. We have the states where set toggles, then we propagate. We have a unique state. In this case, it is when it's constant 0, because then both inputs have to be constant 0. There we propagate again. And we have now the case with a constant line 1. Then we cannot give this information about the inputs, so there we cannot propagate. We build a similar function here. This is just analog to the AND gate. Then the same happens for the glitches. So in this case, of course, the glitch does not get propagated when we have a constant line on one input, because then the output is also trivially 1. So we can again build these two functions here, one for the glitch propagation and one for the back propagation of the probes. So this is basically all, and now's the time I think you have to listen again. So how we can now check our circuits for security. I just want to make a very simple example based on WDDL. If you already listened to the talk about CESIM and LMDPL, you know what's going on here. If not, just two simple things to explain it a little bit. We have a true rail and a false rail for each input. So each input signal is encoded by two variables, one which takes the original value and one that takes the complementary value. And the other point is that we always swap between a pre-charge and an evaluation phase. So first, the whole circuit is set to 0, and then either the true rail or the false rail is set to 1. So how can we check the circuit? First of all, we have to evaluate it. So we need this transitions from one value to the next. This can be simply done. I just made a short example here. Yeah. Then we can evaluate the glitch propagation, which is always 0 here for every gate. This is not a surprise because this WDDL gadgets are free of any glitches, so we also don't expect glitches here. Then we have to calculate the probe propagation back. This is done. You can see here for some gates it propagates, for some not. This is just depending on the input states. And then we can basically place our probe and propagate them according to the functions we had. So in this case, you see one probe propagates as f is 1 for all the gates, and one probe does not propagate at all. So this is basically the model I want to describe. So now we can just formalize it a little bit by an adversary which places up to the so-called relaxed probes, which then propagates as I explained. And based on this, we can define the usual security notions, such as the probing security, or to show composability, we can define probe isolating non-interference. So as it is sometimes hard to do this by hand, we of course want to do this with a tool to have an automated way to check it. So in this sense, we extended ProLead with this model. ProLead is basically a suited target for this model because it's already simulation-based. So the simulations of the circuit are already done. And it can already evaluate the robust deep probing security, also of full masked cipher cores. So we can also feed larger circuits to it, which is probably good because this dual rail stuff can be quite large. But unfortunately, it does not support composability notions at the moment. So we have to rely on the probing security here. And this is the way how it works. It's shifted badly, doesn't matter. So what we have, we gave in the netlist, and at the output, we check if it's secure or not. The step which we basically change is this generate adversary step, because at this point, we generate our probing or back propagation of the probes. This now has to be done for every simulation separately. As it was independent of the data, we could do it before and pre-compute it. This is no longer possible, but So the code is already on GitHub, so feel free to try it out. I would love to have some feedback to it. So let me know if you tried it out. So as a case study, we basically tried to verify the results which are already given in another paper presented at this year's CHES. So here we checked basically LMDPL and CESIM, which are glitch-free circuits. So basically a good target for us because this cannot be evaluated with the robust deep probing model because it assumes glitches. So it would be trivially insecure in this model, but it is not because there are no glitches. And this we can basically check now with our model. These are the the expected results, because Daniel did some measurements for CESIM and for LMDPL. So here we see that we had leakage for CESIM, but no leakage for LMDPL. And we also expect to see this in ProLead, which we did. We evaluated all discussed LMDPL and CESIM protected designs also with ProLead. And yeah, we were able to detect significant first order leakage for all CESIM protected designs, but we were able to confirm the security of all LMDPL protected designs up to a serialized AES version protected with LMDPL. So I come to my last slide and just want to give you the big downside of this model. Of course, this comes at a price to have this more accurate verification. It takes more time with ProLead than the robust deep probing model, and it takes more RAM, of course. It's hard to say how much it actually is. This depends on what kind of circuit you give into. I mean, what I can say is it becomes worse the more you have to propagate back through our circuit. So probably low latency designs can be hard with this model. But however, we could evaluate some designs. You can see it here. We can also see that the overhead is not hard for everything. So it really depends on what you want to evaluate, and it's hard to predict beforehand, unfortunately. So to come to an end, we introduced the robust but relaxed deep probing model, a model which we can basically use to evaluate the same security level as with the robust deep probing model, but with a more formal treatment of glitches based on the process data. We extended ProLead, so you can also use this model to verify your circuits automatically within our new model. But runtime and memory consumption is, of course, increased, so it takes some time to evaluate your circuits. But however, we still think that it's possible even to evaluate larger circuits than an S-box, or for example, full AES design should be doable within our new model. We also proved formally the security of LMDPL and showed that CESIM is insecure as expected. And finally, I just want to give an overview of future work probably here, because as we validated LMDPL in this model, this serves as a proof that such gadgets can exist. So gadgets that are insecure in the robust deep probing model, but secure in our new model. So maybe for your flight back, think about creating new gadgets which are secure in this model. Thank you very much. If you have any questions, feel free to ask.
Thank you for the talk. Any questions or comments? So if you have any questions, so please come up to the microphone.
Yeah, thanks for the talk. So basically, as I understand it, this new model would allow you to basically make gadgets with less registers, because it turns out they're not actually needed to stop glitches. Is that how I understand it? If everything goes right?
Yeah, it depends. I mean, in this model, you have the chance to prove that your glitches stop even if you have no gadgets. If you have no registers, this is what I say. Okay. So you can, of course, build other gadgets with this model, which are maybe more efficient.
Okay, thank you.
Sure. Yeah.
The set of equations that you wrote down there, is basically a way to think about it, that it's like you have a 3-valued logic of like, state 0, state 1, and changed during the cycle?
Sorry, can you repeat it?
I was trying to understand the equations you put down. It seems at least pretty similar to like a 3-valued logic where there's like, state 0, state 1, and changed.
Yeah, in this case, it's just a binary thing. 0 just indicates, okay, no propagation. 1 just indicates that we have a propagation. That's all. So the changes are basically covered by the formula itself. So it just covers for every state we can have, okay, do we have to propagate or do we have to propagate? That's just the only decision we formalized with this functions.
Thank you.
Yeah, also thank you for the talk. If I got you correctly, you basically have to more or less try all possible input combination patterns, or at least all possible input changes, right?
Yes.
Okay, so this basically scales quite badly if we would have a large number of input combinations which all combine at some point, or could combine at some point.
Yeah, possibly. I mean, usually you have gates which not have that much input, so I've tried it up to N4. This is possible. Of course, the formulas become more complicated. That's true. N4 looks not that nice, but it is possible to build these functions. I mean, at least for all gates you would usually use. I mean, if you try to define an AND with 10 inputs, of course, it becomes hard.
Okay, thank you.
Hey, so if you could go back to the slide where you had the green tables with the if Z toggles, then propagates, then blah blah blah. It's quite far, but actually, so I was wondering when you have the statement there that if Z toggles, you always propagate, which means like
This one.
yeah. So if I were which yeah, it's the first one.
Mhm.
So if Z toggles a problem, Z always reveals information about all inputs. But is like if I look just like the Z toggling from low to high, I still have several options for inputs that could lead to that, right? So there might still be some more finer grained.
Very good
Something,
question.
no?
I mean, this table is just a little bit simplified because a toggle from 0 to 1 is not a toggle from 0 to 1, basically, because you can have different delays in this toggle. So you can have this toggle a little bit further, a little bit later. That's the point here. This is not given in this figure, I know.
Right. So okay. So they could be slightly different, these two.
They can.
But maybe they can be the same, right? Like if you could somehow argue that they're always the same, then you cannot distinguish.
I mean, if you have a chance to prove that, yes.
Okay.
Of course.
Thanks. Yeah.
Short question, please.
Okay. Yeah. So it's very interesting, this like conceptual analysis that you can relax the probing model and this allows more freedom. But this probing model is kind of like conceptual, but also we know it works well because we evaluated many designs that are secure using it. If you try to be a bit adversarial and try to synthesize circuits that are secure in this model and see if actually in practice they are, if you could them to break under some kind of like layouts or these kind of effects could break in practice even though you're secure in the model.
Sorry, you have to repeat it again.
The question is, do you think if it's possible to get a secure model, a circuit that is secure in the relaxed model, but in practice wouldn't be secure under some layout constraints and so on?
I mean, of course, this model does not cover everything. For example, coupling is completely excluded for sure. If this answers your question, I mean, yeah, so of course, if placement and routing plays a role, coupling comes into the game, which is not considered here, then you of course can find probably some geometry which is not secure. But this problem you also have for the robust probing model, of course.
So in terms of practical experiment, you did mainly LMDP, LNCSIM, right?
Yeah.
Okay, thanks.
Yeah, we started with this because it makes sense here because we have this problematic with the glitches. That's the point here why we tried LMDP, LNCSIM. Of course, you can do other designs with it.
Yeah, makes sense.
Sure.
Okay, let's thank speaker again. Next talk is titled Compress, Generate Small and Fast Masked Pipeline Circuits. The talk will be given by Richard and Gaeton. Please take it away.
Hi, thanks for the introduction. So I'm here to present the paper Compress, Generate Small and Fast Pipeline Circuits. And together with my colleague Gaeton, we will give the presentation. So just very briefly, this is the last day of the conference. So I just want to talk at a little high level about what we're doing to set the context. So imagine we have a secure algorithm that we've proven secure in practice, and we want to take that and implement it onto a cryptographic device. And when we do this, when we switch from theory to practice, we have all these physical effects that we have to take into account, such as EM radiation, power, or temperature. And through these side channels, so-called side channels, one can deduce the secret key and ultimately break the device. And then we have this important principle that algorithms may be secure in theory, but when implemented, they turn out to be insecure. And over the years, many people have come up with several countermeasures, and one of the most well-studied ones is masking, or in this case specifically, we talk about Boolean masking. And the idea here is that we have a secret variable x, and we want to split that into these shares. And each share operates such that if I combine them all with some operator, in the case of Boolean masking, this is the XOR operator. When we combine them all, we get back the secret value. And the goal, the idea here is that these shares make it exponentially harder for the adversary to break the device. So now the adversary needs all D wires basically to get X. And then later, people came up with these so-called gadgets, which are essentially like building blocks. They take the elementary operations, such as the AND gate and the XOR gate, and they express it in such a way that one can build arbitrarily secure, protection orders for these elementary operations. And some very popular methodologies for doing this is DOM or HPC. And then finally, I introduced the notion of composability, which allows one to arbitrarily stitch together these gadgets and still maintain a security proof, and makes it much easier to do formal verification tasks and on more complex circuits. Okay, and despite all of these advances, masking circuits is still tricky. So here we have the Boyer-Peralta AES S-box. This is just a portion of it, right? The real one, the full implementation takes about 130 equations. And on the screen here, you have all about 64. And already, maybe it makes your head spin to see all of these different equations, and masking this by hand, to implement this by hand in hardware is a quite challenging task. And maybe you have already done this, and so you know what kind of the labor involved here. And one problem is that it's tricky, and then if you make a mistake, then you could end up compromising your entire device. And since we're dealing with hardware, it's quite expensive to make mistakes in general. All right, so then an idea people had was to create automated masking tools. And here, what we do is we take an unprotected HDL implementation, and we want to produce a masked netlist automatically. And one of the first players in the space was the Ajima tool, which can take any masked circuit like a full AES and produce, or any unprotected circuit like the full AES and produce a masked AES on the output. And the way it does this is it takes like a straightforward translation from a elementary gate and replaces that with a masked gadget. Of course, there are some other optimization tricks that they employ, but this is the core principle behind that tool. And then later, Momin et al., what they did was they instead tried to focus essentially on pipelined Boolean circuits. And you can think of that as just the AES S-box, for instance. When you have an S-box like here in these equations, every time you have a multiplier, you have to include some registers, as you've seen in the previous talk. And these registers employ some latency, and that has a detrimental effect on performance. So what we want to do is when we deal with these S-boxes is have some sort of pipelining to recover some of that performance through via throughput. And the way that this tool worked was that they employed HPC2 gadgets. They have some asymmetry associated with these gadgets, and they use some greedy heuristic to optimize the latency to fulfill this pipeline. And in the subject of this talk, we introduced the compress tool, which again focuses on these pipeline Boolean circuits. And what we do is we have several different optimizations in the terms of scheduling and gadget choices to further build more efficient pipelines. And with that, I will introduce the tool. So compress takes a constraint solving approach to achieve the optimal circuit implementation. So what we do is we take 4 inputs. The first is the latency. So this is the number of pipelining stages you would require for your design. The next is the set of gadgets that you can use. So I'll talk more about that later and how we can employ that. Then we need the description of the circuit. So like these are the list of Boolean equations that we've seen in the previous slide. And finally, the costs of the gadget. So this is how many gates it requires to implement and the area per bit of randomness required. And on the output, we get an area optimized circuit that's pipelined and in the form of a Verilog netlist, which you can then integrate into a larger design. All right, and here is just a diagram of how this tool works. In red is the inputs, in yellow are the optimization steps, and then blue are the artifacts or results that you get out of the tool. All right, and just to visualize what a masked pipeline circuit is, here is a simple circuit that's an AND gate and an XOR gate with 3 inputs and 1 output. And let's say that we want to make this masked and pipelined. So the first step we do is replace the AND gate with an HPC2 multiplier, which performs the same operation. And the XOR gate is now done sharewise across the shares individually. We just omitted the sharewise XORing part because it's not important for this slide. All right, and then now if you notice the triangle edges on the HPC2 gadget implies some asymmetry in the output. So this HPC2 gadget takes 2 cycles to compute its result. So now we have an imbalance on the 2 inputs, and a designer may not find this suboptimal, especially when you consider the throughput of this circuit. So what one does is they would add a pipelining stages to the other 2 inputs. So now that the throughput of the circuit is increased, and we recover some performance there at the cost of these registers. And that's the core principle of pipeline circuits and doing this in a masked way. And what we have done with this tool is try to create some special optimizations that occur when you design these and generate them in an automatic way. And with that, I talk about some of the optimizations that we employ. So I will only talk about a few of them that are easy to visualize and explain, but we have several more in the paper, and I invite you to check that out. So here, let's talk about first the gadget selection. So here we have an AND3 example. So this is a 3-input AND gate, and it's implemented purely in HPC2 gadgets. You can see that from the number of triangles or the clock edges, you would require 3 clock cycles to compute the output. And next, one improvement over the HPC2 gadget was this HPC3, which is a low latency version. At the cost of some randomness, you gain 1 clock cycle. So here, you can see that this now takes only 2 clock cycles at the cost of some more randomness. And the compress tool is able to choose these gadgets freely, right, and still produce the same result. So now we've mixed a HPC3 and an HPC2 to still get 2 cycle latency, but the overall randomness usage has decreased. And when we think about how much area it requires to produce 1 bit of randomness from a PRNG or whatever, it's important here that we actually have more savings of area overall. Another trick that we use is gadget replication. So say, for example, we have an XOR gate with 2 inputs and 1 output, and all of these nets are registered. What one can do is that instead of having these 2 pipelining registers on the output, we can simply recompute this later on, since the inputs are available in a deeper pipeline stage. And since in most cell libraries, registers are more expensive than XOR gates, it makes sense here to just recompute rather than forward. And then another trick that we do is gadget decomposition. So here is the internals of an HPC3 gadget. And what it does is it forwards one of the inputs to a later cycle via register internally. And if such a situation arises where that net needs to be forwarded to a deeper pipeline stage from outside of this gadget boundary, so to say, what compress can do is just eliminate one of these registers without cost of security, because essentially this net is the same. And then finally, the last one I'll talk about today is computation scheduling. So if a situation arises where you have an XOR gate, like in the previous slides, one can simply, and if that output of that XOR gate is just simply forwarded to a register, it may make sense just to eliminate that register and move that XOR later down the pipeline. All right, and with that, I invite you to check out the paper where we have more optimizations discussed in more detail, especially on all of these 4 that I've shown you. And with that, I'll invite my co-speaker, Gaetan, to talk about the actual area numbers that we achieved from all these optimizations.
Yeah, so once you have a nice tool, you want to run it. So we want to take example. The first one is looking at the ASS box. Simple one, okay, so that's a very big table. We won't have time to cover it in all detail, and there are even more state-of-the-art and stuff in the paper if you really want to dive on all the details. I'll just highlight a few numbers here regarding latency. So our new approach is able to match the state-of-the-art, which is AGMA using only the HPC3 gadgets. So that's really like really state-of-the-art for ASS boxes. But it uses about like half of the randomness of this AGMA HPC3, or like a bit more than half, thanks to being able to use more HPC2 gadgets than HPC3 gadgets. Also, if you look regarding the area, if you take only the pure core area for the S box, this is like all the best of the state-of-the-art regarding all the generic auto designs. And if we, on top of that, adds the area needed to generate the randomness, here we assume that we use a Trivium PRNG for that. This is the best area next to DOM. But the issue with DOM is that it doesn't have composable security properties, so we don't have a security proof at higher order that it works. So we know it works at first order because it has been verified by tools, but at higher orders, it starts to not be verifiable by these tools, so we don't even know if it's secure or not. So that's really interesting. That's like through optimization, we are basically roughly able to prove with composable designs the cost of previously non-composable designs. So we have better security guarantees for essentially the same or better price. If we look at specialized first order designs, so there have been a lot of works in the past to optimize this. And then it happens that on composable design, we are also able to match or even do better than threshold implementations, and all these designs have been really optimized. So it's interesting to see that now the progress of automated tools is such that we can at least match the current hand optimized designs for both first and second order. So now that we have a nice S-box, we were happy to integrate that into 32-bit data path full AES. So I won't compare too much to the state of the art. I will refer you to the paper for that, just to let you know about these numbers. So like including the PRNG and everything, first order masked AES here takes 86 clock cycles and 25 kilogate equivalent. And you can see that for higher order, it's still costly but reasonable. As a matter of fact, I think like the latency of this is similar to what you find in OpenTitan, but like the cost at the fourth security order or the third security order is similar to the cost of the first order OpenTitan design, comparing to another open design AES. And all of this comes with full security proof, machine checked using the full verif tool. So if you want to see more about that, there is the link. This is maintained, documented with data sets for site analysis on this. So if you're interested, don't hesitate to look at. And as a preview, this will be really like complete AES design. We are developing like larger key size, inverse, and so on in the same package. So now let's move beyond the AES. I'll skip all the results on Skinny that are in the paper to go to 32-bit adders. So this is really relevant if you look at implementing SHA-2 or implementing lattice-based crypto. Every time in masking, you need to do like arithmetic to Boolean conversion, and then the other way around. A very common approach is to use adders and in many other operations. So here we are comparing compress on various architectures. So the first one is triple carry, so the simple series of full adders. And then the other three are different architecture of carry saved adders that are designed for like lower latency in general designs. And they also achieve lower latency in mask because they have lower hand depth. So this is the cost. I would say like one interesting feature is that if you look at purely the area, the more costly at the first order masking is a bit maybe unexpected. So you could expect to have the cheapest to be the ripple carry adder, which is, since it has the least amount of logic, but actually it's not. It's the Van Crook adder, which is like a medium latency one. It uses more AND gadgets, more XOR gadgets than the ripple carry, but importantly, it has a third of the latency, which means that like it uses fewer registers, because like the ripple carry is a state of about like between 64 and 32 bits masked to save, and you need to store them across 31 clock cycles. So that's a very big pipeline, many registers. Reducing the latency, even though we use more logic, reduce the total number of registers to such an extent that we reduce the total cost. So this is clearly a win-win situation to go there. Of course, at higher orders, the AND gates start to dominate over the registers, and then the ripple carry adder may become more competitive. Of course, like compress is not limited to 32-bit adders. It's very easy to generate other sizes of adders. Like with another generator circuit, you just set a parameter and you get all your adders performance. That takes like 3 minutes or 5 minutes to run to generate them. Then optimizing with compress, you can put a threshold, but you get very decent performance result in rotation in half an hour. So if you just need adders, please check it out. So as a conclusion, Compress is really this like generic optimization framework, constraint solving. We put a bunch of constraints, we put a lot of freedom, ways of implementing different ways the things, and then the computer selects what's the best solution. So already our set of gadgets and solutions and optimizations and kind of degrees of freedom that we let the optimizer choose among is already interesting and competitive with the state of the art in masking, but we could clearly add new ones. And looking a bit beyond just compress, I think the general framework of using this like trivially composable masking scheme using Pioneer or similar definitions, it is very comfortable because it frees you to from thinking about security when you are in the bigger grand scheme of things on the composition. You don't need to think about it, and that gives you a lot of room to, okay, I want to do kind of optimization. As long as my gadget satisfies my basic security definition, I know I'm going to be okay. So you can do a lot of things. And actually, by growing bigger and more specialized gadgets, we see that we can increasingly get better and better performance over time. If you look at, for instance, the family of HPC gadgets, I don't know how many are in the literature now, probably about a dozen. And all of them are unique trade-offs. So if we start exploring, very often we find a performance corner that's interesting. So here, examples in this paper, we have a gadget that implements this Toffoli gate. We have gadgets that separate inner domain part versus cross-domain part, and that enables to reuse logic across gadgets. And all of that is within this arbitrary composable framework. So that gives us like a lot of flexibility to optimize. Lastly, all of this is open source. You're an artifact. In the artifact, we'll find another Git repo with the tool. It's Python, very easy to run. All the data, if you want to generate others, if you want the S boxes, it's there. Please check it out. And with this, it concludes my talk. Thank you for your attention.
Thank you for the talk. Please come to the nearest microphone for the question or comment.
Thanks for the talk. I have a question about actually the tool. Yeah, I mean, you explained it, and Compress actually tries many different combinations to find the best solution with respect to the latency and, of course, low area. And if I'm not mistaken, the question is whether that actually the compressor tool is written in a hard-coded way for these gadgets, for the HPC2 and HPC3 or any other gadgets. Yeah, I mean, if we have a gadget in the future, should somebody actually change the code to use the new gadget inside the tool, or no, you have some kind of a plugin that, okay, you hadn't introduced a new gadget and then, okay, the program can run?
It's mostly plugin. If so essentially the way it works is you have a file that describes all the possible gadgets. It describes their latency characteristics, and it describes the feature they perform.
The user has to provide this, you mean?
Yes, you need to tell you that HPC3 uses 1 clock cycle latency and does the AND gate. HPC2 is 1 and 2 cycle latency and does the AND gates too. Of course, but that's you need to provide. But then the tool is automated.
But the other cases, I mean, you move, for example, the XOR, and then the things chart, for example, XOR. I mean, you refer already some of the results. I mean, not you, but your co-author to the paper, that some optimizations actually are shown in the paper, that some XORs can be done afterwards and before the some XOR, some registers. And these are very dedicated, to my opinion, to the gadgets. And these can be also provided externally?
Partly. So the way we do that is provide a new set of functions. So for instance, we have a function that describes only the cross-domain part of AND gate and the inner domain part of AND gate and then XOR. And that's provided in the description of the gadgets. But then what the tools knows is that if it says, oh, I need an AND gate, I can either implement it as an AND gate or as the composition of a cross inner domain part and XOR of the tool. So there is a bit of logic in the tool. Also, like for putting together the XORs with the AND gates into Toffoli gadgets, that's hard-coded in the tool, because like you need to be able to shuffle and use like associativity of the XOR to do that optimally. So a bit of that is in the tool. The tool is like non-trivial code, but it's, I think, around 600 lines of Python code.
Okay.
So it's like a big script. Should be possible to touch and add stuff.
Okay.
I won't claim it's easy, but it's feasible.
Yeah, fair enough. Thank you.
Other comments, questions? Okay, let's thank speakers again.